Okay, so from the name of this model, you may think linear regression can only be used to deal with you know, the sample that looks like linear. Okay, but in reality, okay, linear regression can be used to you know, to fit like a nonlinear data. Okay, so we can extend. Okay, we can extend the linear regression. Okay, to add the powers of each feature as new features. Okay, and then train a linear model on this extended set of features. Okay, this technique, okay, we call it polynomial regression. Okay, so of course, to demonstrate the polynomial regression, we first need to have a data set, right? So we try to generate some samples based on a simple quadratic equation, okay, something like this. This is obviously, you can see, it's y equal to 0.5 x squared plus x plus 2. Okay, this is a equation, but we add like some noise, okay, to make this data set a little bit random, and we generate like 100 instances. Okay, so the result look like something like this. I mean, you can probably observe that, okay, this data set, okay, there's a trend something like this, right? Okay, which actually is like you know, it should be something like similar, something close to the equation that we use to generate this data set. I mean, but obviously this data set, I mean, if you use a linear equation, it doesn't look good, right? If you try to draw a line, okay, obviously there's no straight line that, you know, can fit this set of points very well. Okay, so so straight line will never fit this data properly. Okay, so we can use polynomial feature class to transform the training data, adding the square, okay, the second degree polynomial, okay, of each feature in the training set as a new feature. Okay, now because we only have like you know, one feature, so the square term that we add is just, you know, the square of that feature. That's it. Okay, so I mean, I think like it's you know, here we poly feature. Okay, we just use this polynomial feature class. Okay, assign degrees 2. Okay, to pretty much like you know, include like a second degree like a feature in the training set, and then okay, pretty much like we can, with that, okay, we can with that data set, we can just use that data set to do a linear regression, and the result, okay, will give us like something like this. Okay, so the intercept is this, and the x0 and the x the coefficient for x and x squared are like this. So we know like a coefficient for the I mean the bias is supposed to be 2. The coefficient for x is 1. Coefficient for x squared is 0.5. So you can see that this is coefficient for x squared. It's close to 0.5. The coefficient for x is close to 1. And well, the bias is 2, but now it's 1.78. So this is close to the equation that we use to generate the data. Okay, so if you draw this line, okay, this the line that we use we generate. I mean with the linear regression, okay, this quadratic equation, I mean shown on the figure looks like this. So it captures the trend of all these data points pretty well, right? Okay. However, and obviously we can use this one to do predictions, okay, in the future. But however, if we we can there are multiple features. If there are multiple features, polynomial regression is capable of finding relationships between features. Okay, so for example, if we have two features, say x1, x2, okay, and if we generalize to square, okay, now for this example we only have x, right? So the square, the second order is just x squared, okay? But if we have two features, x1, x2, then not only we introduce, by using like a polynomial class, okay, not only we introduce x squared, x1 squared, x2 squared, we also introduce x1, x2, okay? So if we say we introduce the order 3, what happens is that we are going to have x1, say we have two features, x1, x2, then, and you said like order to be 3, then what we are going to have is x1 squared, x1 cube, x2 squared, and x2 cube, as well as x1, x2, x1 squared x, and x1, x2 squared. All these intermediate terms. Okay, this polynomial regression will automatically generate all those terms for us, all the combinations of features up to a given degree. Okay, so this is like what's going to happen. But for the example, because we only have one feature, so it only generates like a x squared term, and so if you transform an array containing n features, then what you are going to get like this many features, n plus d, the factorial divided by d factorial of d. Okay, so it's going to be a times n factorial of n. So it's going to be a lot, okay, of feature that you are going to add. Okay, so beware of the combinatorial explosion of number of features. Okay, so this is like just need to be aware. Okay, it's not just going to add like just square term. It's going to add like the interactions between like different features. Okay, so if you perform high degree polynomial regression, you will likely fit the training data much better than with plain linear regression. Okay, so linear regression, it would if you don't use polynomial regression to generate like the second order, obviously it's going to generate a line, right? But that line doesn't fit very well. But if you use like if you generate like the second order, a polynomial, then it as I showed earlier, it looks much better. But how about if we use like a 300-degree polynomial model? Supposedly like the higher the degree, the better fit of the model, right? It's going to give us smaller errors, supposedly. Okay, but what happens? Let's have a look. This is a linear regression. A linear line that we are going to get with this data set. Okay, and as I previously discussed, it's not going to perform very well. This red line, and the quadratic form give us pretty nice trend of all these data set, these data points. Okay, as I already showed you earlier. Okay, but if you have if you try to generate a 300-degree like a line to fit this all these points, what you are going to get is this green line. is this green line better than the blue line? Any thoughts? How many of you think it's the green line is better than the blue line? How many of you think it's not? It's worse than the blue line? Okay. How about those who never raise a hand? You don't have opinion? Okay. I mean, I expect you guys to express your opinion. I mean, it's okay to be wrong. I mean, that's fine. Okay. But anyway, okay. Yes. Okay. Let me make this very clear. Okay. In the data science, okay, regardless, it's machine learning. Here we are still discussing machine learning, okay? But even though it's machine learning, okay, but even for the future, okay, we are going to talk about deep learning, okay, regardless deep learning or like some simple machine learning algorithm, okay. What we care about is the trend of the data, okay. When you see the trend of the data, obviously this quadratic form captures the trend pretty well. I mean, this blue quadratic line, okay, actually is better than the red line for no question about it. It is also better than the green line. Why? Because green line actually, if you look at the green line, it actually pick up not only the trend but also the noise. Remember, I mean, when we generate those points, we intentionally add some noise into it, right? And those noise, okay, should be considered just as background noise, white noise, because we use Gaussian distribution to add those noise, okay? They should be considered just background noise. But if you use a model with 300 degree, yeah, it not only pick up the trend, but also those noise, okay, which shouldn't be considered in the trend of the data, okay? So yeah, I mean, in this case, when the model capture not only the trend but also the noise of the data, we call this overfitting, okay? And if the model is not complicated enough to capture the trend of the data, for example, like this linear equation. This linear equation model is too simple to capture the trend of this data set. This is exactly what we say underfitting. Okay, this concept is very important. Okay, this is the reason I discuss polynomial regression. Really, polynomial regression should be covered in machine learning, which is considered as prerequisite of this class. But unfortunately, I'm not sure if, I mean, how many of you have taken the prerequisite anyway. So the reason I want to discuss this is to talk about overfitting and underfitting concept. Okay, so this high degree polynomial regression model is severely overfitting the training set, okay, while the linear model is underfitting it, okay. So if the model overfits the data, okay, another way to call it, okay, one way to call it is, well, the model is overfitting. Another way to call it is that the model does not generalize very well, okay. Okay, the model that will generalize best, okay, is the quadratic model. I mean, the other models, I mean, no matter it's overfitting or underfitting, they normally do not generalize very well, okay. So, I mean, so when you consider the complexity of your model, okay, this is something you need to put in mind, okay. In the deep learning, to be honest, okay, yeah, there are some tasks. I mean, you should determine your model based on the complexity of your task, Okay, some tasks are complicated, and or it has a it has a lot of data set, and your model should be reasonably complicated. Otherwise, your model will, you'll have problem of underfitting. Okay, but to be honest, the most of the time in the deep learning field, okay, the problem is overfitting, because it's very easy to come up with like thousands or even tens of thousands of parameters in a deep learning model, as we will discuss that in the following chapters. So when a model has so many parameters, it's easy to overfit the data set. Okay, so just want you to be aware, okay, the overfitting concept. Okay, so when the model is overfitting or underfitting, we have some issue. But the situation for underfitting, let's talk about how we can determine, how we can tell a model is overfitting or underfitting first. Okay. One way to avoid, to look at, to be able to, get an estimate of the model generalization performance, or you can say it's overfitting or not. Okay, is to use a cross validation. Basically, if you have a data set, you can break it into k sets, and to use each set to train your model, and then to see the average of the performance of the model. But this approach is normally, okay. Let me be clear. Okay, this k-fold cross validation is more suitable for the machine learning field. Okay, like for example, like the one that we talked about, like regression algorithms. Okay, but for deep learning, okay, this approach is probably not going to cut it. Okay, because in the deep learning, we a lot of time we need like a lot of data. So, and the training a lot of time takes a lot of time anyway. So, dividing the data set into k-folds, for deep learning is rare. It's rare, to be honest. Okay, but because we are talking about the ways to see if model is generalizing very well or not. So we have to cover cross validation. Another one is to look at the learning curve. Okay, so this learning curve, okay, can be used to see if a model, including the deep learning model, okay, is overfitting or not. Okay, so what happens is like, okay, on the learning curve, okay, you are going to draw two lines. Okay, normally, okay, when you have a data set, you divide it into maybe like 80% of, to be a training set, and another 20%, okay, half of them to be validation set, half of them to be test set. Okay, that's normally what you do, but the percentage may vary a little bit, but it's normally like that. Okay, but anyway, okay, so when you train a model, okay, you can draw the accuracy of the training set and the accuracy of validation set. Okay, and to see if the model overfits or the model like underfits. Okay, so the y-axis represent like the performance or the accuracy. Okay, here we use RMSE. The y-axis we use the training set size. But in deep learning, a lot of time, the x-axis is like a number of iterations for the learning curve. Okay, but yeah, it could be training set size. Okay, if we are talking about machine learning model, or for deep learning, as I said, okay, we use like a number of iterations. Okay, so you can see that, okay, at the beginning, okay, the training set, okay, accuracy is very high, okay, and the validation set accuracy, goes. Remember this is RMSE, so the higher the worse, okay, because this represents the error. So the higher the error, the worse the model, obviously, right? So at the beginning you can see, because the model is only constructed based on very few training instances. Okay, so obviously the model will fit only those training instances very well, because it's very unlikely that your model doesn't have the complexity to deal with maybe 2 instances, right? Your model must be able to deal with, for 2 instances you can draw a line, right, to fit those 2 instances perfectly, right? So at the beginning you can see its RMSE is close to 0, right? But once you have like more than a few instances, the RMSE of the training set, of course, increase. And for the validation set, because you use validation set, you are using the validation set to, which do not appear, those entries do not appear in the training iteration. So you use those to see like the performance. So obviously, like at the beginning you have the worst validation performance, but eventually when you have more and more instances for training, okay, these 2 lines should sort of like getting close and close. Okay, and in general, I'm not saying always, but most of the case, okay, the error for the validation set should be slightly higher, okay, than the error you get for the training set, because after you use training set to train the model, right? So the model, the error, okay, you estimate, from the training set should be slightly lower than error you estimate, from the validation set. Okay, so this is like a, the learning curve, like you normally see. Okay. I think I already explained this slide. So this is like the situation where like your model, okay, but this is situation where you have underfitting. Why we say it's underfitting? Because, okay, yeah, even though you don't see the problem with these 2 lines, but the RMSE, this error, is very high. Okay, it's very high. It doesn't go down. It doesn't go down. Okay, if your model is like good enough to capture the trend, supposedly you should the RMSE, yeah, these 2 lines should be close, but they should also getting lower. Okay, so this is the underfitting situation. Okay, so how about overfitting? This is the situation, okay, that we use a 10th degree polynomial model. Okay, actually we use this 10th degree polynomial to fit this this point. Not 10 degree polynomial is not like a 300 degree polynomial. So it's not as bad as this green line, but still it obviously, remember our data set was generated by the polynomial equation, right? So degree of 10 is still too much, right? It's still too much. It's still overkill. So the result is still overfitting. So in a sense, in the case of overfitting, okay, you can see because it has a degree of 10. So the first 10 instances, it's not going to give us any error for a training set because we have perfect fit. for the first 10 instances. Well, the degree is 10, so we can fit the 10 instance perfectly, okay? Okay, for the training set, okay? But as the number of instances go up, okay, you can see like the MSE actually, okay, these two lines, okay, are not getting very close, right? They are not getting very close. The MSE actually in the training set, it's actually much better than you can see compared with this one. This is underfitting, remember? So we have higher MSE result. But for the overfitting, I mean, no matter it's a training set or variation set, yeah, I mean the MSE value is reduced. Okay, but these two lines do not, they are not getting very close. The distance here is exactly caused by the model picking up the noise. Okay, because like well, just like here, okay. I mean, supposedly because remember the variation set does not appear in the training set, right? So you can sort of treat like a variation set as a new point that's generated around this point. So you can imagine, okay, those new points must appear somewhere in this quadratic form, right? But when this curve is like something like this, okay, this 300 curve is, okay, a lot of time actually it's, when the point is close to this curve, actually you are going to get a much worse, error than this quadratic form, right? So that is the reason. That is the reason we have a worse validation error, okay, in learning curve. Okay, why we have this gap? Okay. So error on the training set is much lower than with a linear regression model and blah blah. I think I've covered all this. So you can use the learning curve to sort of determine, okay, overfitting and underfitting. When the model is overfitting, the error doesn't go down, okay, or like the accuracy doesn't go up enough. And if model is underfitting, overfitting, then the training error and the validation error, like there will be a gap, okay, after the model training, which is caused by the model picking up the noise. Okay. So an important theoretical result of statistics and machine learning is the fact that model's generalization error can be expressed as a sum of three very different errors. Okay, so there are three errors, the error. Sorry. Let me put it this way. The error is caused by these three different reasons. Okay, the first one is the bias. Okay, so this part of generalization error is due to the wrong assumptions. Okay, such as assuming the data is linear when it's actually quadratic. So high bias model is most likely to underfit the training data. So this is caused by underfit by the wrong assumption. Okay, so for example, here the first case, this is underfitting situation. This actually we are using the linear model. That's why the first two points are we don't have any error. Okay, and then goes up. So this is like we show the learning curve of the linear line. Okay, this one based on the training set and validation set. Okay, so So obviously that's the reason. I mean, the reason is caused by, we assume the data set, the trend is linear. So that's, even though, I mean, remember I told you like last week, like before you know anything, with your, if you get a lot of data, okay, before you do anything, you can try to use a linear regression to fit the model. Okay, I'm not saying the linear model is always good, but supposedly you can use a linear model as like a baseline. Okay, and if something you get is worse than linear model, it's not, you shouldn't consider that. Okay, so linear model is normally what you consider first, but obviously, I mean, you could like end up having like a wrong assumption. Like actually the points are, in this case, I mean, they are generated by the quadratic equation. Okay, but so the use linear model to fit it obviously is not good enough. Okay, so that's like the first source of the error. The second source of error is a variance. So this part is due to a model excessive sensitivity to small variation in the training data. So this variance, a model with many degrees of freedom, okay, is likely to have high variance and thus overfit the training data. So for example, the overfitting is normally caused by this variance error. Okay, this gap, okay, is caused by this variance. Okay, the third one is called irreducible error. Okay, this irreducible error is due to the noisiness of the data itself. So this one, okay, look at the keyword irreducible error. You don't want to reduce this error. If you want to reduce this error, most likely you are going to end up with an overfitting model. Okay, so this is something you want to keep in mind. Okay, so the only way to get rid of this error is to do data cleansing, or data cleaning. I mean, whatever you call it. The data cleaning is one of the important research field. Okay, I had one paper on this area. Okay, that was published in like a top tier conference. Okay, so this is like one area that is like a very important area. Okay, there are still many ongoing research on this. Okay, for example, you can fix the data sources. Okay, for example, like broken sensors, detect and remove outliers. I mean, some outliers. I mean, if you know they are outliers, you can remove them safely. I mean, to reduce this irreducible error. Okay, here, okay, when I say irreducible error, I'm saying that you cannot use the model to get rid of it. It's not like you cannot use data cleansing. Okay, data cleansing, I mean, it's different thing. Okay, it's different thing. So increasing a model's complexity will typically increase its variance. So this one, if you increase the data, the complexity of the data, complexity of the model, okay, most likely will increase the variance and reduce the bias. Okay, so conversely, reducing a model's complexity increase the bias and reduce the variance. So these two, okay, overfitting and underfitting, they are trade-off to each other. Okay, but there's a balance between them. There's a balance between them. As I said, like for example, the example I show you, okay, because we know those data sets are generated by a quadratic function, right? But in reality, I mean, when you get a data set, you don't know the underlying complexity of the model should be something, should be what? I mean, you have no idea, right? So yeah, so basically there's a balance between these two. But how to find the balance? Well, you can gradually increase the complexity of the model without overfitting. Okay, if you find your model overfits, then you know like you reach like a certain, I mean your model is too complicated. Okay, but as I said, like in deep learning, okay, most of the time you are dealing with overfitting, not underfitting, because the model is has a lot of parameters in deep learning anyway. Okay, and also, okay, when your model is overfitting, there are several ways you can deal with it or mitigate this problem. Okay, such as like you know, to regularize the model. What is regularize the model? Okay, basically it's just to constrain the model. Constrain the model. Remember, the overfitting is caused by the model having too much freedom, right? Okay, so in order to avoid model having too much freedom, you can put some additional constraint to avoid overfitting. That's the basic idea. Okay, the fewer degrees of freedom the model has, the harder the model will be for overfitting the data set. Okay, a simple way to regularize a polynomial model is to reduce the number of polynomial degree, obviously. Okay, but for linear model, regularization is typically achieved by constraining the weight of the model. So the following regularization technique that I'm going to discuss, okay, especially, okay, the first two, ridge regression and the lasso regression, okay, which are also called L1 and L2, have been used in many areas, not only machine learning, okay, but also deep learning. As for elastic net, I mean, well, you can treat it as like a combination of L1 and L2, okay? I mean, so they basically are used to constrain the weight, okay? So what are them? Okay, okay. So ridge regression, also called Tikhonov regularization. Okay, this is, okay, you just try to add this alpha times theta I squared, summation of theta I squared, times an alpha to the cost function. To the cost function. We call this L2. Okay, that 2 basically comes from these 2. Okay? So because it's a sum of squares, right? So this thing must be positive, right? This thing must be positive. Oh, by the way, alpha is also positive. Okay? So this whole term is positive. So when you add this one to the cost function, obviously the cost function increase, right? But remember, when we want to we use the gradient descent, okay, we are reducing the value of the cost function, right? So so not only we reduce the original term in the cost function, we also reduce this term, right? So reducing this term put certain constraint to these theta i's. Okay? So that's the basic idea of the ridge regularization, or L2. Okay? So this is the first one. Okay? And the second one is called well, this is like just want to give you an idea, okay? I mean, ridge regression cost function is going to be MSE plus alpha times this one. Okay, so you can see this is basically just like the original term, okay? Well, times like 0.5 times alpha, that's it. So the other one is called let me show the first, I mean, the result of the ridge regularization. So depending on the value of alpha, the higher the alpha is, the more constraint it put to the theta I, okay, because of this cost function. The higher the alpha means this term become more and more important in the cost function, right? So when you use gradient descent to reduce this cost function, okay, more constraint will be put on this term. Okay? So that's like the basic idea. So the higher the alpha, the more constraint you have for the theta I. So what is the result? The result is something like this. Okay? So for the linear situation, linear situation, where alpha increase from 0 to 100, you can see that it becomes, more, the linear equation becomes like more and more flat. Okay, what does that mean? The flatter linear equation means the slope is close to 0, right? The slope is close to 0. The slope close to 0 means what? Remember, the slope is theta 1, right? It's a coefficient for x1, right? Okay, coefficient of x is theta, right? Which is theta 1, which is the slope, basically. So when alpha is large, it will gradually reduce that theta to be closer and closer to 0. And here is a more telling example. Okay, here we are using higher order, okay, to approximate these points. Okay, so original, this blue line is when alpha is 0, meaning we are not constraining. We do not put any regularization, okay, into this model. But when alpha is only 10 to the power of -5, it's a very small value. You can see what happens is that, okay, this variance, this curve become less less variable, right? It becomes less variable. It becomes much smoother, right? Again, it's due to the constraint you put to the theta, okay, to all the theta terms. When alpha is 1, it's a much larger constraint. Okay, you can see it reduced to almost a linear line. Close, but not exactly, because here we still see like a rise of the equation. But you can see the equation become much smoother, right? It's this is just to show you the power, the constraint power of the ridge regularization. Okay, well, yeah. So we can let me finish this. Okay, so as with a linear regression, we can perform ridge regression. Okay, by computing a closed form equation. Okay, or by perform the gradient descent. Okay, so pros and cons are the same. Okay, so following equation shows a closed form solution. Okay, so but as I said, like we care more about the gradient descent approach because after all, we are using this for the deep learning class. So we can also show how you can write this ridge regression into the stochastic gradient descent. Okay, so yeah, you can see you just set the penalty to be L2. Remember, I told you ridge regression is another more well-known name is L2. So you just set it to be L2. So basically, you just put the ridge regression into the SGD regressor, which is a stochastic gradient descent. Remember, I told you. So basically, that's it. So another this is closed form solution. I don't think that's any different than this one anyway. Okay, so well, So that's I think we are running out of time. So that's today we finished like ridge regression. Next time I will talk about lasso. Okay, and I will also discuss like a difference between ridge and lasso. But today, I mean, unfortunately, I don't have enough time. Originally, I thought like I should be able to cover lasso and the difference between these two. But yeah, that's fine. Let's talk about this next week. Okay. Again, just want to remind you, please go to E-class to download the first project and find your teammates as soon as possible. Okay, if you haven't done that. Okay, so any question? If no question, I will see you guys next week. Okay, and we don't have class the week after next. Okay, just want to remind you guys again on that. Okay.